Alright, it's day 256 off the grid, and we've had a bit of sun today, so the batteries have kind of been loving it. And I've also finished the latest Beltane song, Cape Evil 5, Solstice Wizard, which I'll be uploading tomorrow to Beltane's Reverb Nation page, and that was the most important thing I did today. But I've actually had some time to do some more electronics, so this is what I've been doing. Now, in my previous post I was talking about this special circuit that I've been working on to improve the function of a cheap charge controller. In fact, it's a sticker that I have that's already in use, but this is further improving its functionality. Yes, it looks like a mess at the moment, it's all clip leady and stuff, but a lot of it's actually done. So we'll just have a quick look here. Here's the control board, and here's the MOSFETs. Okay, what this does is something quite special. Number one, it will convert a common positive, i.e. a switching negative charge controller like all those cheap ones are, to one that actually switches on the positive, on the high. It's like high side switching. And I'm still in fact using N-channel MOSFETs to do this, just by doing a really simple method. I've got this auxiliary battery here which jacks the gate voltage of the MOSFETs up like 12 volts above the high voltage rail, or the battery, the normal battery voltage. So it'll work for 24 volts, it'll work for 12. I've rigged it up as 12 at the moment, so this is, if you like, our main battery. This would be the battery if this was a real system that was going to be charged by the solar panels. And this is what I call the boost battery. It's a battery that only has to supply a minute amount of current to run the circuit. It could be a small solar panel because it only has to run during the day when there's solar charging. I've got one of these circuits, a similar one, a simpler one already in operation, and I just use dud lantern batteries from Bafgil's parents. Her dad runs a one of those dolphin torches that use the 6-volt batteries, and when the batteries are too flat for his torch, I can use them for that, and they last for months, in fact years in that role, because these circuits consume such small amounts of current. So the boost battery can be basically anything. So there's no real need to go to a lot of trouble to try and develop some kind of switching boost circuit which can create further problems when this is such a simple solution. In fact, you could buy a brand new 9-volt battery like this, and that would do the job for the shelf life of the battery. But anyway, so first function the circuit does is it allows you to use a cheap charge controller and switch on the high side, and for that matter to switch a lot more current too, because these MOSFETs here will handle 20 amps no problems. You could parallel MOSFETs, which is not what I've done here. I've got other purposes for these which I'll say about in a minute, but you could parallel all those 3 MOSFETs. In fact, that's what I did on my other circuit. So the amount of current you can switch is, it's not really limited by anything. Of course, the more MOSFETs you parallel, the greater the gate capacitance, so you might get to a point where they don't switch as cleanly, so you're getting a bit of linear action. But if you put that on a big heatsink, I mean bigger than that, who gives a shit? It'll still regulate. But the second function of this controller is that it's actually like a real-time diversion controller, if that makes any sense. So when the sticker decides the battery's full and stops supplying a solid current and starts going into PWM mode and starts feeding the battery pulses, during the off pulses the circuit can divert that power from the solar panels somewhere else. And this is basically what the circuit manages. There's an extra transistor, this one down here, that handles that. And this MOSFET here over on the right with the yellow clip to it is in fact that diversion MOSFET. So it's really simple. It's really just a kind of you know, an inverter circuit really. When this one's on, that one's off. When that one's off, this one's on. All controlled by the gate signal from the charge controller. But I've done it without any ICs because I like using transistors. I've got a lot of them, and I like things simple. I like the idea that something, if it breaks down, I can always find parts to fix it, you know, even if the shit hit the fan, you know, or whatever. Transistors are good like that. And I know exactly what's going on in every single component in the circuit. It's not like, well, I know what the circuit's doing, but I don't quite know what the inside of this chip's doing. You know, I like to be able to know what is actually going on with my circuits. So, I mean, you know, I do use black boxes, of course. I mean, after all, the signal that I'm taking from the charge controller is coming out of essentially a black box. But, you know, stuff like this, I like transistors, but that's just me. But using transistors is easier to do things like level shifts, because the control signal that comes out of the sticker is about 8 volts above the normal ground above here. But yet I'm switching MOSFETs that are, you know, like up to 10 volts above the high voltage of the batteries. So when you're starting to do things like level shifts, and transistor circuits I think are a lot easier than using logic chips. So there we go, that's my arguments there. And one transistor and a resistor makes an inverter. They're not really that difficult to make, are they? So, having said that, let's have a quick look and see how it works. So it's running at the moment, and this 9 volt battery here is just pretending to be the charge controller. It's quite a flat 9 volt battery, so it's putting out about 8 volts, which conveniently is about what the gate signal is from the charge controller that I've tapped into. So this meter here is showing a voltage. That voltage is the voltage that's being fed to the gate of this MOSFET. At the moment, this battery is not connected, that's why this probe's hanging free. So that simulates the charge controller during the space phase of the PWM. So because the charge controller is basically shut off at this point, all the power from the panels is being diverted through the auxiliary circuit. Now suppose the main battery gets flat and the charge controller turns on and creates a mark. We can simulate that by joining this up. Watch what happens. No gate signal, it's gone slightly negative, but that's just one of the idiosyncrasies of the circuit. And I don't know if I can show that, but just under that clip there's a Zener diode, and when it's forward biased, that's what's causing that clamping to be at negative 0.7. Otherwise it would go right down to negative 7. And you don't really want to drive a MOSFET too negative, but 0.7 volts is fine. So therefore, MOSFET on, MOSFET off. Charge controller off, charge controller on. So if I'm careful, I can shift this and show you the signal. Oh, she's a bit, should have a smaller clip. Show you the signal at the oh, there we go, at the other MOSFET. Right, so probe's disconnected, so charge controller off, and as you can see this one is about 0. It doesn't actually dip negative because it's wired quite differently. So charge controller off, charge controller on, charge controller off, charge controller on. Now bear in mind, oh, clip just fell off, but you get the idea. Now bear in mind that this signal was from 8 volts above the ground rail, totally from the ground rail. Whereas that voltage that we were looking at on the meter is actually a voltage above the positive of the battery, because the voltage has to be above the positive of the battery in order to allow these MOSFETs to work as high side drivers. So that's basically it really. I don't think there's much more to say about it. These are just simple NPN signal transistors. second-hand ones, I think. They had solder on the leads. I built it on Vero board, which is a bit dicey when you're kind of designing with the soldering iron, as it were, and you're not entirely sure if everything's going to work. Well, part of the circuit was already proven, the bit that just simply allows you to turn a charge controller into a positive switching one, but that extra bit, the inversion phase of it, I hadn't proved. That was all done by theory, and then I just soldered it on and hoped that it would work, because Vero board is a really good way of building up proven designs if you don't want to go to the bother of making a printed circuit board, which I never do. I can never be bothered, I generally don't make circuits complicated enough to really justify the effort. So Vero board works well for me. But if you're building something where you think you might have to make a few changes to the components, well, Vero board is pretty shitty for that. If once you start desoldering things, trying to change resistor values and change this and change that, well, things can go to pants really, really fast. So often when I'm building a project where the prototype may be the final unit, but I'm not sure if it will be, I find construction methods like this, like tag strip, much better. Oops, dropped that one too. Hopefully not where I can't find it, but I'll look for that after the vid. Yeah, tag strip. And the other thing I like to build with, actually, another thing that's good is, I don't know if I've got an example of it right here to pull out, is perforated board, like Vero board, but without tracks. So you just stick the components through and then solder the wires together underneath. Those kind of boards are quite good because you can get a near Vero board look, at least on the top. The bottom kind of looks a bit of a rat's nest, but if you need to change components, it's relatively easy to take them out and make changes. So yeah, that's kind of a better way to do it. So Vero board, no, but I was lucky with this design because as it worked first time, no issues really there, and I kind of knew it would because theoretically it was a pretty solid design. What else can I say about it? I shouldn't say anything more because this video is becoming very long, but a couple more things. Oh, the resistor values. My original circuit, I used really, really high values like 120, 130 kilo ohms for the collector resistors and stuff, because I wanted to maintain the life of this boost battery, and that works fine, and it's been working fine. But for this one, I kind of thought I'd try experimenting with lower values, which is still pretty high, but lower values, just so the MOSFETs can be switched a bit more cleanly, a bit faster. So I dropped the values down to about 33k, and I happened to choose 33k merely because I had a bandolier of 33k resistors that I found on the ground down here. It must have fallen off at some point, so I nearly trod them to pieces, and I found them lying down there and thought, okay, I'll use them. So there you go. You know, sometimes resistor values in electronics are really arbitrary. You just kind of got to get them within a range that is suitable, you know. But, you know, I'm pretty happy with this. I haven't had a decent go with little fiddly electronic projects like this for quite some time, so I'm quite happy to have done this, and it's a very useful circuit. You know, I like useful things, so maybe not in the next couple of days because I've got other things to do, and the Equinox is coming up, which is Beltane's 2015 Equinox, or Spring Equinox recording. So, but at the next chance I get, I'll be starting to put this together, and I'll be installing it in the shed on the 24 volt system in place of what I've got in there at the moment, which I have made other videos about, so you can see what I've got in there, which is it has already got a MOSFET sort of extension slave power device kind of thing like this as already, but it just still switches in the negative line, so it's a lot simpler. But this will be much better when I get it going, and the reason why I'm so keen on it is now as we roll on to, you know, spring equinox next week, you know, it's going to be, you know, high spring, the day of Beltane, in another 6 weeks, and after that it'll be the summer solstice, so we're well into the lighter seasons now, and yeah, we're getting a lot of excess power from this 24 volt system that's basically going nowhere, and it sort of pisses you off when then a cloudy day comes along and you're like, wow, if that power had gone somewhere, we could be using it today. So this will allow that. That's why this is an important circuit. Right, I've just broken the 15-minute mark, so I'm going to stop now. So what, that's day, what did I say? Actually did the sum. Day 256 off the grid.